All right, I want to define what's called a leaf of a graph, and it doesn't have to be on a tree, but a leaf of a graph is any vertex of degree 1. So there's only one edge that contains that vertex. Okay, so let's say I look at this particular graph right here. Excuse me. And let's connect it with these edges and ask the question, which of those vertices are leaves? So like this one right here is not a leaf, and that's because it's got two edges. But this one is a leaf. It's a degree 1. So that one right there, that one, that one, that one. So there are 4 that would be considered a leaf of a graph vertex of degree 1. Okay, so theorem. Every tree of at least 2 vertices has a leaf. So we're guaranteed that every tree that has at least 2 vertices must have a leaf. So let's prove that every tree, that is every connected acyclic graph, has a leaf. So let's let T be a tree such that the number of vertices, so the cardinality of the vertex set, is greater than or equal to 2. I'm going to let P be the longest possible path in the tree, which means that it has to have at least 2 vertices, because if you have 2 vertices and it's a connected graph, those two have to be connected. So your longest path is at least 2 vertices long. So let's just, for notation, let's let P equal V naught is adjacent to V1 is adjacent to ... is adjacent to VL, so that L is greater than or equal to 1. So you have at least 2 vertices, at least 1 length in the path. Okay. I claim that if P is the longest path, V naught and VL are leaves of the tree, which of the tree T. So in order to prove that they are leaves, let's assume for a contradiction that V naught is not a leaf. And you could do the same thing for VL. I'm going to do it for V naught, which is going to give me that there is a leaf. But let's assume it's not a leaf and show that leads to a contradiction. Now, if it's not a leaf, that means it's not degree 1, which means the degree of V naught is greater than or equal to 2. In other words, there has to be something adjacent to V1. Let's say it's called X. So there exists an X that's not V1. So, right, since V naught is adjacent to V1, there has to be something else adjacent to V naught. I want to call that X, and it's adjacent to V naught. But X can't be on the path. And the reason it can't be on the path is that if I do put it on the path, then I can end up back at V naught with a cycle, right? It would be a cycle. P would be V naught to V1, all the way to, eventually to X, and then I would be able, from X, to go back to V naught, which makes this a cycle. But you can't have any cycles because this graph is a tree. So we know that X is not on the longest path. So if you assume V naught is not a leaf, something else besides V1 is adjacent to V naught, but that thing is not on the path P. So what I'm going to do is I'm going to make a new path, call it Q, and stick X at the very beginning, X before V naught. So let Q, because X is now adjacent to V naught, put it at the beginning, and that goes all the way from V naught to VL. The problem is Q is now longer than P, but I assumed P was the longest one, so that's a contradiction. So no matter how long the longest one is, if the first one is not a leaf, then there's always going to be a longer one, which means there has to be a leaf. So V naught is a leaf, therefore every tree has a leaf. Proved. The next theorem I want to show you, another property of trees, says that if T is a tree and V is a leaf, then T minus V is also a tree. Anytime you remove a leaf from a tree, it's still a tree. Right? If you remove a degree 1 vertex from a tree, it remains a tree. Now, the only way something could no longer be a tree is if it's either disconnected or it becomes cyclic. That is, there is a cycle in it. So proof. I got to prove that if I remove a leaf that it's still got no cycles and it's still connected. So wish to show T minus V is a tree. Now, since T is acyclic, removing a vertex cannot create a cycle because that needs more edges, not less. So T minus V is also acyclic. So all I have to show is that T minus V is connected. Removing a leaf is not does not create a disconnected graph. So let A and B be elements of the vertex set of T minus V. I need to show that there still is a path from A to B. Since T is connected, we know there is an AB path in T. So let's assume for a contradiction that V is somewhere in that path, so that if I remove that vertex, I no longer have a path, which would mean it's disconnected. So P goes from A to V to B. But that's impossible because that means the degree of V is at least 2. But V is a leaf, so that is a contradiction. Since the degree of V is 1, then V cannot be on the path, which means there's still a path from A to B in T minus V. Thus, it's still connected. Proved.